Look at some let's look at some examples of surface area here. And remember, we're going to revolve about either the x-axis or the y-axis. So I'm going to give you the first example of a problem you can see. You got the function y equals x. Now this would be over the interval from 0 to 4. And they want us to rotate or revolve about the x-axis. Okay, so if we consider, again, let's just kind of go back with what we talked about. Here's my x-axis. Here's my y-axis. This is the curve. Y is x. We're going to revolve this about the x-axis. So we're going to rotate it this way. Okay, so now what this does for us, if you remember, is this creates, if we go from 0 to 4 here, we're going to take this little strip here, this portion of the curve, we're going to revolve this portion of the curve about the x-axis. Okay, so if you remember correctly, last time what we talked about was we're going to need a ds. So we're going to need that ds there. Rotating that is going to give us a surface area, and it's a lateral surface area. And remember, we're going to use this 2 pi r ds business. So our ds, we're going to have to figure out what to use for ds right in here. So in our formula, we're going to need a ds. So we need that distance. But we're also going to need the radius. So let me draw you a picture again from last time. We're going to get this little portion ds here. Let's get this whole distance, by the way, let's go back a quick second. This whole distance is s. But what I'm going to need is a ds. So if I go back, erase that portion, we need that little ds there. That's the ds that they're talking about. So I'll put it back. That whole thing was actually s. So here's my increment of the arc length, really. And remember, if we rotate, we need also a radius value. This is my radius. And so what do we know about this radius from last week, right? If this is a vertical length, what does that mean my radius actually is? Right? What's this r going to be? R here is going to be what? The y value? Is that true? So what r, your radius, is a corresponding y value. That small increment ds that we're looking at, we're rotating about this x-axis. So we're creating, like we talked about last week, this little rubber band strip, if you want to talk about that strip. And that's what we're looking for in this example. So r here is the y value. We already know that the y value here is actually x. So our radius will be equal to x. So in our formula, we're going to have the surface area become the integral from 0 to 4, 2 pi, not r, but x, and then I have this ds. So remember last week too, what do we use for ds? Okay, so we're going to need a ds here, and we have two versions of ds. Anybody remember the versions of ds that we have from last week? What do we use for ds last week? Right, our ds is going to be the square root of 1 plus y prime squared dx, or it's going to be the square root of 1 plus x prime squared dx. This is for my ds. So which ds do you think would be probably a good idea to use, you think? The first ds or the second ds? What do you guys think? Why would the first one be the good one to use? Because remember, you're going to have 4 versions of this surface area, so why would this first one be pretty good to use? Anybody know? Well, let's take a look. If you pay attention to this portion here, that's an integral that involves the x variable. So if you're going to replace your ds here with the first version, well, you're going to get a function here that's in terms of the x variable, and you're going to integrate in terms of that x variable. So remember what y is here. Let's not forget y. Y is x. So our y prime here will be, what's the derivative of x? Isn't that 1? Okay. So when we use that first, whatever you want to call it, ds here, right? That's going to be the square root of 1 plus 1 squared dx. Okay? So now we can integrate in terms of, here's from 0 to 4, 2 pi x square root of 2 dx. We can integrate in terms of x. Notice that you have some constants here. So I'm going to pull out the constants. 2 pi square root of x, or square root of 2, x dx from 0 to 4. And that's going to give us 2 pi square root of 2. Looks like it's x squared over 2. And we evaluate this from x is 0 to x is 4. So I get 2 pi square root of 2, 4 squared over 2, minus 2 pi square root of 2, 0 squared over 2. And this portion on the right side is 0. Remember that? And now we get, what is this? 2 pi square root of 2, 16 over 2. Or simply, it looks like it's going to be 8. So I get 8 times 2 pi square root of 2. And what do we get here? What do you guys see? Anybody know? Is this going to be what? 16 pi square root of 2? Okay, so I want to point out to you that the ds that you have to use in this case here is the first ds, where y prime, or we should say y is a function of x, so y prime is a function of x, and you're integrating here in terms of the x variable. Okay, so if you have that vertical line, you're going to use the y value, the y coordinate value, for your radius, and then you get that rubber band strip we were talking about. And this is an example of how to use your surface area formula. Yes?
So the second one, isn't it dy?
Oh, you're right. The second one, thank you. You got to wake up. That is a dy, and however, we have to use dx. Okay? Good observation here. Yeah, that's the dilemma you're going to be in, which ds to use. And you're going to see as we go along here with these examples how to go about that. So that's our first example. Let's look at another example here. You can find the surface area, and you get y here is x cubed. And this is going to be over the interval 0, 2. You're going to revolve about the x-axis. So in this example here, if you said, we're going to take this curve, kind of the x cubed curve, 0 to 2 again. Okay, we're going to revolve this about the x-axis again. And notice we're going to look at this little increment here. That's our ds. And we're going to revolve this about the x-axis. So you're going to get a curve. Here's your rubber band again. And again, we're going to need that radius. So the radius here, here's a vertical line here. Here's my radius. R again is the y coordinate value. So for every x value in this region, y is that radius. Okay, you guys okay with that? You got your integral of 2 pi r ds for surface area. And again, our radius is the y coordinate value, and that's x cubed. Now, that tells us which ds to use. Because when I integrate and you have a function of x there, you're going to actually need the right ds. So ds here is going to be the square root 1 plus y prime squared dx again. And so let's see what we get now. Y prime will be 3x squared. Okay, and so 1 plus y prime squared becomes 1 plus 3x squared squared, or 1 plus y prime squared becomes 1 plus, looks like 9x to the 4th power. And so you need the square root of 1 plus 9x to the 4th power here. That's going to be our ds. So our integral now is 2 pi x cubed. Our ds is 1 plus 9x to the 4th power dx. And I guess this is from 0 to 2. Okay, you guys okay with that? And that's how you're going to use this ds, the right ds that gives you a function of x to integrate. But the question now is going to be, how can we integrate? Right? How do you integrate this? What method do you guys use for integration? I'd say use what? What are you going to use? Good job. You're going to use u sub. Right? You're going to let u be the whole thing of 1 plus 9x to the 4th power. What's the tip-off that you use u sub? Anybody? What's the real tip-off that this is a u sub situation? Go look at the power here. Look at this power here. This is a 4th power, and that's a what? 3rd power. So when you have that 4th power and you have that 3rd power, this is your tip-off for a u sub. So in this case now, let's see what we get. Since u is 1 plus 9x to the 4th, notice du dx is, what's 9 times 4? That 36x cubed. Or we can say that dx becomes du over 36x cubed. Okay, so our integral now will be 2 pi x to the 3rd power square root of u du over 36x cubed. So the x cubes go away here, and you get this integral of 2 pi square root of u du over 36. Now, we could do a couple of things. It might be good for us to recall our limits here, right? This is x is 0. This is x is 2. So we need our limits in terms of our u variable. So we're going to go back now and replace 0 here for u. And that's going to give me a limit here, a lower limit of 1. And we're going to replace 2 here. And let's see what happens. It looks like we're going to get, what's 9 times 2 to the 4th power? Do you guys know what's 2 to the 4th power? 16. What's 16 times 9? What is it? What's 16 times 9 plus 1? It's not mumble. Is that 144? 1 plus 1? Okay, good job. I think it was 145. Okay, it looks like we're okay. Is everybody okay with that one? Looks like we're fine with that. Okay. Whatever. Now we get what? Pi over 18 integral u to the 1/2 du 1 and 145. So this integral, pi over 18 u to the 3/2 over that 3/2, u is 1, u is 145. Pi over 18 times 2/3 u to the 3/2 U is 1, U is 145. So it looks like I get pi over 27. Double check. U to the 3 halves, 145. Now get pi over 27, 145 to the 3 halves, minus 1, if I use a parentheses here, 1 to the 3 halves. So I get pi over 27 times 145 times the square root of 145 minus 1. And notice your surface area here is positive, and that kind of makes sense. So surface area should be positive. Double check. Can I simplify that square root of 145, by the way? I don't know. I'm not sure. How many times does 5 go into 145? Looks like it's 29 times. Is that 5 times 29? Yeah, I think we're done. Nevertheless, this is another problem with surface area. And as you guys can see, even when you're given a simple curve like x cubed here, right, a nice simple curve like this x cubed, you start to get a complicated surface area integral. Even if it's just x, it's a lot easier when it was just x. But as we look at other examples, the integral is going to become much more complicated, and we're going to have to remember probably, some past integration ideas just to solve these. So let me give you another example here and show you that we got y here, 4 minus x to the 2/3 power 3 halves, and this is going to be over, they're going to say over the interval 0 to 8, and again, they want you to revolve this about the x-axis. So let's take a closer look to our surface area 2 pi r ds. We talked about this last time, right? So let's note a few things. That first of all, my y is a function of x. Okay, you guys okay with that? And what you guys noticed was when you rotate about the x-axis and you're given y as a function of x, this here, your r is your y, or it's your f of x. Is that true? So you might want to think about this and say, all right, surface area will be the integral of 2 pi f of x ds. You're rotating about the x-axis, a function of x. Y is a function of x here. What ds do you think you're going to have to use now? Right? We got to use a ds. So I need a ds. Which ds do we have to use? You're going to use a ds that gives you, right? ds will be, you need the ds that gives us a function of x here. So even though that's y prime is going to be, remember, the derivative of that, of f, and this is a function of x. So if you're going to have a function of x here, this portion for your ds, that also has to give you a what? Function of x. Because you're going to integrate, and notice that this again is over that dx. So that's going to be your ds. Now, a little bit easier said than done, because let's find out what ds is, right? So what was our y function? Do you guys remember here? In this example, we get what? 4 minus x to the 2/3 power times, or raised to the power of 3 halves here. You're going to need that derivative. Okay, you guys with me on that so far? We're going to need that derivative. And then we're going to square it, we're going to add 1 and take the square root of it. Now, these problems, if you can integrate, they're specially chosen. Okay, so let's find the right derivative now. Notice what the derivative is going to be. 3 halves, 4 minus x to the 2/3 times, if you want every detail, 3 halves minus 1 times what? Do you guys know? What is it? It's going to be times, what is it going to be? In other words, what am I really asking you guys? Don't forget about what? Chain rule. So chain rule is going to give me, looks like it's going to be a negative 3/2 x to the 2/3 minus 1 now. Okay, you guys okay with that one? So you're going to have to use some chain rule here. Oh, we made a mistake. You guys didn't catch it? Negative 2/3, sorry. Okay, so let's see what this derivative is. We're going to have 3/2 here. We're going to be careful. 4 minus x to the 2/3. 3/2 minus 1, isn't that 1/2? And then I got a negative 2/3 x to the negative what? 1/3. Okay, you guys okay with that one? And we can do a little better. We can simplify. Tell me if you guys agree. This is negative 4 minus x to the 2/3 power raised to the 1/2 times x to the minus 1/3 power. Does anybody know what I just did here? What did I do? I multiplied my 3/2 with my what? 2/3, and I kept the negative sign. Okay, you guys okay with that? Because I'm going to have to do some algebra. The algebra is we're going to have to square this y prime. And squaring this y prime, 4 minus x to the 2/3, 1/2 x to the negative 1/3. We're going to square this. We're going to get 4 minus x to the 2/3 power times x to the what? Negative 1/3 power. So double check that algebra. Okay, your biggest thing that you're going to do here is the algebra. Double check. Am I okay with that? You guys remember what you guys know what I just did? I took this 2 and I distributed. I distributed that power 2 to both of these bases. And if I square a negative 1, what happens there? Looks like it's positive. Is that right? Okay, you guys okay with that? Okay. Now, do you guys know what I'm going to do with this now? I'm going to distribute. So I'll get my y prime squared to be 4x to the minus 1/3 minus x to the, what's 2/3 minus 1/3? Is that 1/3? Oh, I forgot to square my what? There we go. That's where it is. Thank you so much. Yeah. Okay. That's supposed to be what? Anybody know? That's a 2. Good. That's going to make all the difference in the world. Okay? Because everything I've done here, I've done already, and I have it here in my notes, which is good. You always have to be prepared. Double check. So yes, we're going to distribute those powers. You now get 4x to the minus 2/3 minus what? What do you got? What minus? Is that minus 1? Okay. Now 1 plus 1 prime squared is 1 plus 4x to the minus 2/3 minus 1, or simply 4x to the minus 2/3, okay? Take the square root. This is going to give us, what does this give us? The square root of 4, the square root of x to the minus 2/3. This gives us 2. Is that true? And what does this portion give us? X to the minus 2/3 power raised to the 1/2 power. Or you get 2x to the minus 1/3 power. Okay. And this is my, what I'm going to put into my radical. So let me kind of highlight this. Okay. And go back here, I guess. 2x to the minus 1/3 power. Where does that go? That goes right here. 2x to the minus 1/3 power. And is this a ds or is it a dx? Dx. Good. Now, what's the function again? The function again is this scary function you see here. Okay, so let's put this all together here. Okay, this here is my f of x, or my y. So it's 4 minus x to the 2/3 in parentheses raised to the 3/2 power. So we're going to have to integrate. Okay. So what was that function? 4 minus x to the, was it 2/3? You guys know? Is it 2/3 raised to the, what was it raised to? 3/2 times x to the negative 1/3 dx. And what were the limits on that? Do you guys remember? 0 to, is it 8? 0 to 8, and these are in terms of x. Okay, let's double check here. You're right, 0 to 8, okay. Let's double check. Is there, I think there's a 2 there, right? Are we missing a 2? Well, we're missing a couple of things. Let's go back. The 2 is there, and we have a 2 pi there, okay? So this is what we're going to use for our ds, right, or at least partly. There was a 2 there, and now let's pull out the constants and say we have a 4 pi here, integral 0 to 8, 4 minus x to the 2/3, everything raised to the 3/2, x to the minus 1/3 dx. Okay, a nice integral here to perform this morning. Now let's see, like I said, I did all these the other day. What do you guys think would be a good idea to use? Anybody have any idea what might be helpful? Good, u sub. So we're going to use u sub. Okay, let's put that here. U sub. Now, we're going to let u here be what we have here. So u will be 4 minus x to the 2/3 power. Then du dx will be negative 2/3 x to the negative 1/3 power. Is that true? All right, we need to solve for dx, I guess, or you can notice something here, right? Can we say negative 3/2 du is x to the minus 1/3 dx? Could you say that? Do you guys know what I'm talking about there? If I multiply both sides by this, right, negative 3/2 goes away, and then multiply both sides by dx. So what I'm saying is that this portion right here in my integral is really negative 3/2 du. And this portion is u. Let's remember the limits. When x is 0, that means u is going to be what? 0. Is that right? Let's write it here. 4 pi integral u 3/2 times negative 3/2 du. When x is 0, u is 0. When x is 8 now, what happens when x is 8? What does u become when x is 8? Anybody know? Oh, I think we made a mistake. Go back here. Okay, we made a mistake here. This is what we're looking at right here. See if you're awake. When x is 0, what does u become here? U is 4? Okay, so we get a 4 down here. Is that true? Now, what happens if I change this to an 8? What does u become now? U becomes 0. Okay, you guys okay with that? No big deal. We're changing our limits because you're going to integrate in terms of u. So let's see what we get here now. We get negative 4 pi times that constant 3/2. We're going to integrate from 4 to 0, u to the 3/2 now, du. Now, I guess we can say this is negative what? Is that negative 6 pi? Integral 4 to 0, u to the 3/2 du. What do you guys think? Is that okay? Okay, now I'm going to say this to you. Is this valid? What did I do? Do you know what I did? What did I just do here? You see this negative sign? You see my limits? I can switch my limits. What's the price you pay for switching your limits? The sign there, yes. And now it looks like we're pretty good. Is that right? Okay. So we have 6 pi u to the, what's 3/2 plus 1? Is that 5/2? Divided by 5/2, u is 0, and u is 4. Okay, you okay with that? So we get now 6 pi times 2/5, I guess, u to the 5/2, evaluated from 0 to 4. Double check, because I'm not really awake yet. There's a lot of drama getting this up and running, I guess. Like always. 12 pi over 5. Now we get 4 to the 5/2. Put this in a bracket. Minus 0 to the 5/2. And I get 12 pi over 5. Do you guys know what 4 to the 5/2 is? Isn't it 2 to the 5th power? And then this is minus 0. So I get 12 pi over 5 times 32, I guess. Okay, you okay with that? So what's 12 times 32? You guys are going to have to help me out this morning because I'm not awake. You guys will make me do my, okay. 32 times 12, 4, 6, 2, 3, 4, 8, 3, 384. 384 pi over 5. So let's make this a little bit nicer, 3. Okay, a nice surface area question. And now let's see what we could do once we're awake. Okay, you guys ready for a nice problem now? Another nice situation? Anybody have any questions on this one? No? You ready for a good one? Okay. You sure? All right, here's something that is kind of interesting. Let's give you another example here. Y is sine x. And again, it's over an interval here. I'm going to give you a different notation. This is 0 to pi, okay? And they're going to want to revolve again about the x-axis, I believe. So, revolve about the x-axis again. So we're going to go over some of these questions here. These are kind of things that people can see, I guess, and they wonder about. And I got like so many of them to do. It's amazing. Okay, so amazing. So let's try this out. 0 to pi. So, I mean, should we draw the curve? Do you guys want to, you know what I'm talking? You guys want to draw the sine curve? Sort of. Then that 0 to pi here. Revolve this about the x-axis. And again, if you wanted, just focus on a strip, maybe right here. Right? That's our ds. And notice yet again, we need that radius value. Here's our r value, because the strip they give you that rubber band, I guess, okay? And r again, my art skills are not so good. R again here is 1, but r is variable. R again is your y coordinate value, which happens to be what? Sine. So if you go back again for your surface area formula here, right? That's supposed to be a rubber band strip. Sorry. 2 pi r what? ds. So r again, let's put r in. That's y, or f of x. That's a function of x. My ds has to give me a function of x, and we're going to integrate in terms of this x. So this ds here, square root 1 plus y prime squared dx. You know, we're going to see others. I'm going to give you guys, I'll even record probably later some more examples and everything. Okay, so you guys have a lot of different examples to look at here. You know, because there's essentially some kind of curve like that. You want to see that rubber band strip. Looks ugly, so I'm going to get rid of it. Okay. Anyway. That's what we're looking for here. This r value and r ds. Okay? And we need the derivative. So what is y prime going to be? Do you guys know what the derivative of sine is? It's cosine, right? And then square that derivative. Cosine squared. And then 1 plus y prime squared is 1 plus cosine squared. Take your square roots. So let's see what this integral is going to be. 0 to pi, 2 pi sine x square root 1 plus cosine squared x dx. Let's write that a little better. Okay, so far so good? All right, let me ask you guys a question. What could you use to integrate? All right, what do you think? When you look at this and you say, well, how am I going to integrate this? It depends on what you mean by U sub. It depends on what you mean. When I see this, you want to know what stands out in some ways? Not a U sub necessarily. This portion here stands out to me. You guys know what I'm talking about? You go, what are you talking about? What am I really getting at? This is a version of what? Trig sub. Now, you might want to do the intermediate step, and you're going to say, let t be what? T be sine, I guess. Is that right? So this will be my t, by the way, and this is, oh, I'm sorry, that's not true. Let's go back. It's very much not true. Let's do the intermediate step here. T is cosine, is that right? Because if we're going to have a cosine squared be t squared, t is cosine, so what is dt? What's the derivative of cosine? Minus sine dx. So my dx becomes dt over a minus sine x. So yes, it's going to be a nice trig sub, I guess. But we're going to do the intermediate step, meaning this is the integral now. Let's go back. We got 2 pi sine x square root 1 plus t squared dx will be dt over that minus sine x. And get rid of your signs here. Okay? So, and this is going to be 0 and pi. Now this is x. Excuse me? Oh, sorry. You know, some of this stuff is a real pain like you would not even believe. You have no clue. Sorry, like, Anyway. Negative 2 pi. X is 0. X is pi. And we get the square root now. 1 plus what? T squared dt. Now, what is t again? Do you guys know what t is? T is cosine. Is that true? So, since t is cosine, we're going to have to look at our limits. What's cosine of pi? Is that negative 1? So, this means t is negative 1. Okay. What's cosine now? What's the other limit? 0. What's cosine of 0? Is that positive 1? T is positive 1. Does that look a little backwards to you guys? Say yes. What do I mean by that? You got this integral, negative 2 pi. If we want to be a little consistent here, let's do this. I got negative 2 pi, and I'm going to integrate from 1 to negative 1, square root 1 plus t squared dt. What should I do here again? Switch the limits and take the opposite, right? In other words, you got that negative sign. It's going to be gone if I change my limits here, right? If I reverse the limits. So to let you guys know here, this is when we say it looks like a nice what? A trig sub question. Nice trig sub. Okay? Now you say, what do you mean it's a nice trig sub? Because it's of the form, right? Isn't this of the form a squared plus t squared, I guess? So that's where it's trig sub. What do you guys want to let t be? T be tangent theta. Good. If t is tangent theta, what's the derivative of tangent? Is that secant squared? And that's d theta. And then what do I replace the radical with? 1 plus t squared. What does that give us? That is secant theta. So we get the integral of 2 pi now. Looks like it's secant theta. dt is secant squared theta d theta. 2 pi integral of secant cubed theta d theta. Okay? So what I'm going to tell you guys again now is I have to know what the integral of secant cubed theta d theta is. Now remember what I said before. Isn't it a good idea to have some integrals under your belt? Do you guys remember some integrals kind of memorized that's going to help you? You're kind of like in that spot here. Okay, what is this? What is the integral of secant cubed theta d theta? Anybody know? What is that integral? 1/2 secant theta tangent theta. Is that true? Plus natural log absolute value secant theta plus tangent theta. Double check because I'm not really awake. Right? You guys okay with that one? So, what does this mean then? Don't I have this what? 2 pi multiplied to, bring down the 2 pi then. Let's do it that way. What does this give me as an answer? Pi times what? Secant theta tangent theta plus the natural log absolute value secant theta plus tangent theta. Now, I got a couple of issues with this. Let me put it all over here. Pi secant theta tangent theta plus natural log absolute value secant theta plus my tangent theta. Is that true? Okay. Now let's go back here. Let's remember. What is tangent theta again? So I can say, because we're doing trig sub. Remember this trig sub? We know that tangent theta is t over 1. Is that true? So let's draw the triangle here. Theta. Opposite over adjacent. And this is going to be 1 plus what? T squared. So in other words, what's secant theta going to be? Anybody know what secant theta should be if this is the case? Square root of 1 plus what? T squared. Is that true? So we're going to use this. Tangent theta is t. Secant theta is the radical. So what we're going to go back and do is say secant theta, this is the radical. 1 plus t squared. Here's my t. Secant theta is the radical. 1 plus t squared. Tangent theta is the t. Does anybody know why we need to do this? Do you guys know? We get pi times t square root 1 plus t squared plus natural log absolute value square root 1 plus t squared plus a t. Anybody know why we need to do this? Yeah, go back over here. Look at this. This is t is 1. This is t is what? Negative 1. Is that right? Does anybody see anything interesting here? Can I do anything here with this? I'm just curious, is this integral an even integral over a symmetric interval? Anybody know what I'm talking about? What do I mean by that? What is this? You guys see what I'm talking about? This function here is even. Isn't that true? If I replace t with a minus t, isn't it the same function? So it's even. You okay with that? And then the interval is symmetric from -1 to 1. What does that mean if you're in calculus 1? What do you guys remember about this? Because I just integrated the square root of 1 plus t squared dt, and here's the antiderivative, I guess. So you'd have to evaluate this as f of 1 minus f of -1. Is that true? You guys with me on that? Now, I don't know about you guys. I really don't like doing a lot of work. You know what I'm going to do instead? Tell me if you guys agree with this. Tell me why. I think I can say this is double. And I'm going to get rid of this one and say that this is going to be a what? 0. Can I do that?
Yeah.
Anybody know what I'm talking about? Because over here, all I have to do is double this integral and change this limit to 0. Because the function here is even. Right? F of t is even. So it might save me a little bit of, nightmare, I guess. So let's try this out then. I got 2 pi, and I'm going to replace this with 1 square root, 1 plus 1 squared, plus natural log, absolute value square root, 1 plus 1 squared. Is that plus 1, I guess? Minus 2 pi 0 a square root plus natural log square root of absolute value. 1 plus 0 squared plus 0. And I get my 2 pi now, square root of 2, plus natural log absolute value, square root of 2, plus 1, minus 2 pi. That's 0 plus the natural log of square root of 1 plus 0. Well, I guess it's easy to say that this portion goes to what? 0. And we're going to end up with 2 pi square root of 2 plus the natural log of square root of 2 plus 1. We get to remove that. And I guess that's kind of good enough. Is that right? What do you guys think? Double check because I'm not really awake. Double check. Is that kind of okay? You guys okay with that one? I think that looks okay to me. Anybody find an error on that one? No? You guys okay with that? Okay. I think I'm going to save this one a little bit till later. Okay, let's try this out here. Let's transition a little bit. You guys ready to do a transition? Transition, I said? Yes. Oh, it's what? You know, I'm going to go crazy here. And we may need a power cord today. Anybody have an iPad Pro with them? Or I'm sorry. Yeah, what's the power cord in this thing? Anybody have a Apple laptop with them? No? We have a power cord for an Apple laptop? On them. That's what happens when your daughter uses all your stuff, you know what I mean? She takes it out of the bag. You don't need this. I'm a daughter. Huh?
She tells you that you don't need
No, I'm just thinking out loud because she takes everything and she's just, oh, I guess he doesn't need this because why would he need it? Like, oh my God, Ashley, don't touch my things, please. Okay, well, let's see what we could do. Ugh. Sounds about right. That's what you guys take your dad's things all the time? You know what I'm saying? Oh, that drives me crazy. Really? You guys take all your dad's stuff? Why? Leave your poor dads alone. You know what I mean? You're gonna take his wallet and he needs it. He runs out of gas and he doesn't have his wallet because you took it. That's like how life. You know what I mean? Like, where's my wallet? All right, let's try one here. Okay, we got y equals x squared over the interval 0 to what? 4. We're going to rotate about the y-axis. So let's be careful. And I'm going to say, ladies and gentlemen, don't take these problems when you go home and rotate about any axis you like. Because if you do, you may regret it. We're going to rotate about the y-axis. You guys okay with that? And this is like from 0 to 4. So let me kind of sketch this. Let me rotate about the y-axis now. So what does that mean? Let me get a nice little strip here again. Okay, here's a strip for my DS. There's that DS there. So go from here to here. And so fine, and I rotate that. Notice what happens. We get a nice rubber band, like we've been saying, for this DS. But you guys want to tell me now what's going on here? I'm going to put this thing about my radius now. What's my radius going to be now? R is going to be what? R is going to be the x coordinate value. Is that true? It's horizontal. So in the formula here, integral 2 pi r ds, what's going to happen now with r, my radius? That's an x. That's not y. That's x. Okay, you guys okay with that? So, okay, how does that change things? I still need a ds. Which ds do I use? The one that gives me a function of x, right? Here's a dx. I got another version, right? I have another version that gives me a function of what? Of y. Which do I use? What do you guys think? What do you guys use? The one that gives you a function of what? X. That's the ds you guys use. Why would you use that? Because you got a function of x right here. Okay, you guys see what I'm saying? There's an x there. That's your new radius. In this example, we're transitioning because there's 4 types of surface area integrals. This is going to be r is your radius is x. Now, what happens here is y prime will be, well, what's y prime? That's 2x. What's y prime squared? That's 2x squared, or 4x squared. What's 1 plus y prime squared? 1 plus 4x squared. Take the square root of these things. You're going to end up with the integral being 2 pi x square root 1 plus 4x squared dx. That looks ugly. Let's clean it up. Two pi x square root 1 plus 4x squared, and then that's a nice dx there. And I guess we integrate from 0 to what? 4. Now, why is this a pretty good problem?
Professor,
Yeah.
x squared, y equals x squared,
I'm sorry. Say it again.
take the first equation and you put on top, isn't it y equals x squared?
Y equals x squared. It is true. It is true. Y does equal what? X squared. That's true. That's what they gave you. That's right. They gave you y equals x squared. Okay, probably what people get thrown for at first here is this r value. This is now a horizontal. It's not vertical. So if that's horizontal, that's going to be, your radius is going to be x. If it's vertical, your radius is what? Your radius is y. So you get this integral. That's good because you can now use what here? You use u sub. So you're going to say u is going to be 1 plus 4x squared. And du dx is 8x. So that my dx becomes du over 8x. So let's look at this integral. 2 pi x square root of u du over 8x. Pi over 4 integral square root of u du. Let's see what our limits are. This is in terms of x. X is 0, x is 4. When x is 0, what is u? 1. When x is 4, what is u? What's 64 plus 1? 65. Good. Okay. pi over 4. U to the 3 halves over 3 halves. U is 1 and U is 5. Pi over 4 times 2/3. U to the 3 halves. U is 1. U is 5. So we get, what is this? Is that pi over 6? 5 to the 3 halves minus 1 to the 3 halves. So I get a pi over 6 here. 5 square root of 5 minus 1. Double check. Huh? 65. Thank you. Oh, where did I get this 5? Okay, this is the answer we got a little earlier. However, there is a typo because remember, U is 65 and U is 1. So we're going to replace this here, this here, this here, and this here, I guess. Well, let's plug in what the right value is. 65 here, 1 here. So this is going to give us 65 square root of 65 minus 1. And this is the example that we did earlier in class where we took y equals x squared over the interval 0 to 4. We're going to rotate this about the y-axis, and here's our answer. So let's look at another example here. So for this example, let's take a look at what we have. We want the surface area. Let's find here. Okay. We did x cubed. Earlier today. How about if we do this one here? Y equals x to the 3rd power, 0 less than or equal to x less than or equal to 2. Now let's double check. We're going to rotate this one about the x-axis. Now, if we did this earlier, we may have, let's go back and take a look at some of these problems. Sounds familiar, x cubed here. Yeah, looks like we did this, and that's over the interval 0, 2. Oh, so we did something like this earlier. So let me actually remark about this question here. We did this one earlier, so let's give you just a remark. We rotated this about the x-axis, so I want to talk about this in detail. I'm going to give you guys a remark here, something we spoke about in class as well. What if you had to rotate about the y-axis here instead of the x-axis? Now let's look at some details. Here's a curve x cubed, x-axis, y-axis. So let's look at it this way. We have y equals x cubed. Now these problems are very specially chosen, so we're not going to do this problem again. But what we're going to do here, we're going to rotate this about the y-axis. And I want to remind you, based on our discussion earlier, that if we look at this interval 0 to 2, here's 2, and we rotate this curve, what we're looking to do here in red is there's going to be our increment ds. This is that ds. We're going to rotate this about the y-axis. So if I consider this to be ds here, we get this strip here, this rubber band. And now the radius that we have to use here, this radius r is going to be the x-coordinate. It's not going to be the y-coordinate. So here's my radius, so that when I look at my integral now for the surface area, and I'll put this all in purple, I guess. So the integral of 2 pi r ds. We know that the radius here is x. So I'm going to replace my radius with x. Now the question is going to become, what ds do I use? Well, we're going to use the ds. We always want the ds to be one that gives me an integral that can integrate over the variable x, because I have my x here. This is my dx. I have my x. They gave us y equals x cubed. That's okay, that's fine. So since y is x cubed here, remember that for this particular ds, we need the derivative squared, so that we get y prime being 3x squared. So I want to remind you guys that this is just a remark, like we talked about in class today. Let's get rid of that. We get the square root 1 plus 9x to the 4th power, and that's our part of our integrand. That's part of the ds. So here's what we're going to replace this with. This ds is really going to be the square root here of 1 plus 9x to the 4th power dx. So the surface area integral, if I change how I rotate, this is 2 pi x square root 1 plus 9x to the 4th power dx. And this is still over 0 to 2. That's still what I integrate over. So what happens at times is students get confused, or I should say, they pretty much overlook what's going on here. Rotating about the y-axis, that means that the radius value is just x. That x goes here, and we leave it alone. And since I have an x variable, I need my integral to involve, or we should integrate over dx. So now everything's fine, and this is my surface area, and this is what's going to happen if we revolve about the y-axis. Now, this is a different question than what we did earlier. Earlier we revolved about the x-axis. Now, what happens with these integrals is they're specially chosen. So they're specially chosen so that you can integrate. This particular problem isn't so specially chosen. We can still probably find a way to integrate this. Not be so easy, but we're just going to set this one up and just go over the format that we discussed earlier when we look at some of these curves and we rotate these curves about, any axis. So they're usually specially chosen so that you can actually integrate. And now I'm looking over some other examples. Let's take a look at one we did earlier too. Give you another example. let's say we take the curve y equals 1 minus x squared over 0 to 1. We're going to rotate about the y-axis. This is just like the prior example. This is new. If you guys know what this curve looks like, by the way, it's not that necessary, but let's take a look. This is a curve. This is a parabola. Sorry. That opens down. 0 to 1 here. So we're going to rotate this now, this curve. We're going to rotate this about the y-axis here. So again, we have a little strip. Got this strip here. And we get this rubber band. Change our color. My R here, again, is an x value. So in our integral, so we say surface area is going to be the integral of 2 pi r with ds. Well, r here is x, so I'm going to replace that with an x. Now go back. This function is written here as y equals 1 minus x squared. That's fine. We're going to leave it that way. If our radius was y, then we'd rewrite this as 1 minus x squared for that radius value for y. But it's not. It's the x coordinate. What that tells us is for our ds, we're going to need the version that integrates over the x variable. This is 1 plus ry prime squared. So let's see what we have now. We know that y is 1 minus x squared. And y prime will give us negative 2x. 1 plus y prime squared is 1 plus negative 2x squared, or 1 plus 4x squared. We're going to take the square root so that our surface area, or we're going to replace this with, let's put it in red, this ds is going to be replaced with square root of 1 plus 4x squared. Okay. So we have now the integral 2 pi x square root 1 plus 4x squared dx, and we're going to integrate over 0 to 1. So this is 0 and this is 1. So here's where we're at. This is what we were discussing earlier, and we're going to use now u sub. Okay. So we have u here being 1 plus 4x squared because we have u sub, and that means du dx is 8x. So that my dx becomes du over 8x. 2 pi x square root u du over 8x. Cancel these x's. So we're going to have pi over 4 integral u to the 1/2 du. This is 0 to 1. So I get pi over 4 now, u to the 3/2 over 3/2, or pi over 4 times 2/3 u to the 3/2. This gives us pi over 6 u to the 3/2. Now, what is u? If I go back here, replace this x with 0, that gives me u going to be 1. So when x is 0, u is 1. That's the lower limit. When x is 1 now, if I erase this, that's going to give me 5.
u is 5. u is 5. So I get pi over 6, 5 to the 3 halves, minus 1 to the 3 halves, or pi over 6, 5 square root of 5, minus 1. Now that does look familiar. We may have done this one, well, it looks familiar because we did it earlier in class. This is actually how you would handle that situation when you revolve about the y-axis instead. Okay, let's see what we have next. How about if we take a look at this one here, and we revolve this about the y-axis again. So here's another example. We have y equals 1/4 x squared minus 1/2 natural log x. This is over the interval from 1 to 2. We're going to rotate about the y-axis. So let's take a look at how we go about this. Our surface area, again, is the integral of 2 pi r ds. So if you remember, when we rotate a curve, any curve about the y-axis, right, here's my y-axis, we're going to rotate about this. We're going to get this strip here that creates our rubber band. There's a little strip. We need that ds. And again, stay with me on this. Looks pretty horrible. But we get this strip here. Here's my ds. More importantly, this is my radius, which is x. So what I want to illustrate is that this radius here is simply x. It doesn't matter that my curve is given in terms of y. We're going to leave that radius be x because that's what the radius is. Nevertheless, that tells us what ds to use. The ds that we have to use is the one that can allow us to integrate in terms of the x variable. That means this is 1 plus y prime squared. So since y here, let's go back to see what we have in terms of y. Y is 1/4 x squared minus that 1/2 natural log x. I could take my y prime to be 1/4 times 2x minus 1 over 2 times x. Our y prime will be 1/2 x minus 1 over 2x. If we square this, get 1/2 x minus 1 over 2x squared. One half x minus this 1 over 2x. 1/2 x minus 1 over 2x. By FOIL, we get 1/4 x squared. First term, the outer term is going to be, looks like minus 1/4. The inner term is going to be minus 1/4. And the last term is going to be plus 1 over 4x squared, which is 1/4 x squared minus 1/2 plus 1 over 4x squared. Now remember the effect of adding 1 to this. We've seen this before, and we're going to notice the symmetry here. Get 1/4 x squared plus that 1/2 plus 1 over 4x squared. So here's what's going on here. This is now a plus, where before if we just squared this, this was a minus here. So 1 plus the derivative squared is really 1/2 x plus 1 over 2x squared, a perfect square trinomial. So when you take the square root now of all of that, we get the absolute value. Now this, what's under the absolute value here, this whole thing is positive over the interval from 1 to 2 for those values of x. So we can actually get rid of the absolute value sign and just have this for our radical. Okay? So it's 1/2 x plus 1 over 2x. This is what we're going to use over here. So we'll put this in red. This is my ds. It's 1/2 x minus 1 over 2x. So let's see what happens here with this integral. We get 2 pi x times 1/2 x plus 1 over 2x dx from 0 to 1. This is our surface area. Now, if we factor out the 2 pi and distribute the x, we get 1/2 x squared plus 1/2. This is dx. I can factor out the 1/2, which gives me pi x squared plus 1 dx. X is 0 to 1. I now get pi 1/3 x cubed plus x evaluated from 0 to 1. Don't forget this parentheses. So we get pi 1/3 times 1 cubed plus 1 minus pi 1/3 0 cubed plus 0. So this right side here is 0. I get pi times 1/3 plus 1. Remember what 1 really is? 3 over 3. Surface area is going to be 4/3. Look like it's 4/3 pi. And that's a 4. Do we have the right limit, 0 to 1? We have the wrong limits, 1 to 2. Okay, wrong limits, 1 to 2. Glad I caught it. Let's reevaluate from 1 to 2. Okay, check my notes, and I found that this was the wrong limits. Okay, 1 to 2. So we get our pi now. 1/3 2 cubed plus 2 minus pi 1/3 1 cubed plus 1. Pi times 8/3 plus 2 minus pi times 1/3 plus 1. So this is pi times 8/3 plus 6/3 minus pi times 1/3 plus 3/3. Pi times 14/3 minus pi times 4/3. 10 pi over 3. Now, this is the correct limits with our correct answer. So here's how we revolve about, looks like we revolve here about the, which was this? Y-axis again. And that's going to leave us to a couple of other versions here, a couple of other problems. Let me say this. Let's give you one more example about this here. Let's look at another example. We have x equals 1 plus 2y squared. Our interval is going to be between 1 and 2. We rotate about the x-axis. So again, I want to draw this picture here for us. Okay, we're going to rotate about the x-axis. So here's my x-axis. We're going to rotate our curve. So if we had a curve that looks something like like this, for example, we need that strip, the ds. So if this is that length ds here, here's my ds. We're again going to get this rubber band here over that ds. And that tells us now that this is our radius, and our radius is a y value. So here, r is y. Now using our surface area formula here, we have the integral of 2 pi r ds. We already know what the radius here is. The radius here is y. So I'm going to replace this radius with y. Now notice I have a function here, x equals 1 plus 2y squared. That doesn't matter for our radius. Our radius is y, so we don't have to describe this in any other way other than y. The question then becomes, what kind of ds do we need to have? Well, we need the ds that allows us to integrate with respect to that y variable, because we have a y there. So that tells us this has to be x prime squared. Now that's pretty good because we know that x is, let's go back here, 1 plus 2y squared, because that's what they gave us. Yes, this is over 1 to 2. So I get x prime squared going to be 4y. So 1 plus x prime squared is 1 plus, we got to square this. Let's go back. We get x prime to be 4y. Square x prime. 4y squared. So 1 plus x prime squared becomes 1 plus, making the mistakes here. Square that. 16y squared. So our square root of 1 plus x prime squared becomes square root 1 plus 16y squared. So that means this is our ds, 1 plus 16y squared dy. Surface area. Integral from 1 to 2. 2 pi y square root 1 plus 16y squared dy. And you guys can guess that we are going to use now here u sub. U is 1 plus 16y squared. Du dy becomes 32y, or dy is du over that 32y. So my integral 2 pi y times u to the 1/2 du over 32y. Y's cancel. I get, it looks like, pi over 16 u to the 1/2 du. Now let's remember here, let's be careful. The limits here are that y is 1 to 2. So I'm going to let y be 1 here, and that gives me a u value of 17. So that's my lower limit. If I let now y not be 1, let's let y be 2. I get 1 plus 16 times 4. So 16 times 4 is 64, plus 1, we get 65. So 65 for the upper limit. Lower limit 17, 65 is the upper limit. Okay, let's integrate. Get u to the 3/2 over that 3/2. U is 17, and u is 65. I get pi over 16 times 2/3 u to the 3/2 1765 pi over 24 u to the 3/2 u is 17 and u is 65. So we evaluate here our limits, upper limit and lower limit. We get 16 to the 3/2. We get that 65 and we get 17. So pi over 24, 65 times the square root of 65. Let's write this nice and neat because it's our final answer. We get 65 square root of 65 minus 17 square root of 17. This is our surface area. So that concludes some of the examples we went over in class earlier when we ran out of power. And I'll put this together for you guys, and this is the last surface area.